Hello, Chem One. This is our first PowerPoint that I'm going to go over. It's a lot of repeated information from what you've seen from the videos that I shared later part of last week. However, I wanted to put my slant on some of the pieces to try to help with understanding a little bit better the intermolecular forces. So this is the PowerPoint, or a modification of a PowerPoint that I used last year, talking about the major types of intermolecular forces. Those are the dispersion forces, or the London dispersion forces, dipole-dipole interactions, and the hydrogen bonding. Something that's not listed here is the ion-dipole, but we'll touch on all different aspects. So administrative piece. First off, there is is this dangerous unit assessment going to be on Google Classroom. I think I plan for it to be released shortly after our flex hour this afternoon. You essentially will have 1 week to work on that. It is a one and done, but it is on Google Classroom. You can do it as open note if need be. I just ask that you be honest and not cheat or steal or just Google your answers or ask other people for assistance. Do it on your own, but do it based on your notes and open notes. So be prepared before you sit down to take that. Okay, but that is going to be there. And actually, it's scheduled to be due on Sunday at midnight, 11:55 p.m. Don't wait till Easter, because Sunday is Easter. Don't wait till Easter in order to try to do this test. You're going to make your family very upset with me as your Sunday saying, I have to do this test, I have to do this test. Today, as I'm taping this is Monday. I'm going to mention this in our flex hour today. Get it done. So, this is the last thing that's on the test. That's the intermolecular forces. Again, but this was all covered last week. I'm just trying to clarify some weak points. Okay, so the reason why I wanted to address the intermolecular forces aspect is as it connects to states of matter. Now, I don't know whether or not you're completely aware or whether or not you think this way, but one of the recognitions of what goes on in a state of matter is really just a matter of how attracted the molecules are to one another. If you have a really, really strong attraction between the molecules, say at room temperature when there's a certain amount of energy available and the attraction is very, very strong towards the molecules, then that sample is going to be in a solid state where the molecules are very close together and they don't tend to move very much. They kind of just vibrate. If there's less of an attraction, not a very, very minimalistic attraction, but less of an attraction between the molecules, then that's going to be in the liquid state where the molecules are going to be able to free flow amongst one another, but still they stay close together. And then finally, if the molecules are very, very much not attracted to one another, then that's going to be in a gaseous state because there is limited, if not almost zero, attraction between the molecules, and therefore the molecules will be able to just go use the energy that's in the room in order to spread out and move a amount in the space. Okay, so that's why this is a consideration, is talking about what is going on and how do intermolecular forces tend to impact the state or the type things that go on within a substance. So different states of matter, again, we've touched on this before, and you've touched on this actually in in chemistry, like 6th grade when you did the physical science. Talked about liquids, the difference between a liquid, solids, and a gas. Gases assume the shape of the container and the volume of the container, so they completely fill up the container. They are compressible, so you can squeeze them down. They flow, so they are what's called a fluid. Fluids flow, and gases and liquids are both considered fluids. And they diffuse or spread rapidly across an area. Liquids, they assume the shape of the container, but they do not change their volume. They do not change their volume. They have a constant volume. And they're virtually incompressible. Now, obviously, you can compress them a little bit. There's a little bit of space between them, but virtually they're incompressible and they flow. And the diffusion, when it does happen, is slowly. Think in terms of like dropping a drop of food coloring into some water. Sooner or later, it does spread throughout the container, but it just takes a little bit of time. And then finally, solids, they have the shape and volume that's set. They do not change. They do not, the shape doesn't change, the volume doesn't change. They do not expand. They are virtually incompressible. They do not flow. And if there is any diffusion, it's going to be very, very slow. Sometimes you might see somebody drops like a stain on a piece of cabinet or a piece of wood or a piece of rock, and slow and steady, it does tend to ooze and make its way across that particular container, but it's very, 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 very slow. Okay. So which state of matter is something going to be in? Well, here's where we overthink states of matter. There are two different main attractions, two different major types of energy involved in determining what state of matter a material is in. There's the kinetic energy that the molecules have. That means how much they're moving around and how much energy is there. And the attraction between the molecules. So if you look at the table on the right-hand side, it talks about the fact that in a gas molecule, their kinetic energy is so huge, it is significantly greater than the attraction the molecules have for one another. And because their kinetic energy is so huge, they're so moving around so much, then they are going to be in the gas state. When the kinetic energies and the energy attractions are pretty close to one another, I mean, they say comparable, then you're going to be in liquid phase. And when the energy of the attraction is so large that it completely overrides the kinetic energy of the molecules, then that's going to be in the solid state. It's all about relative amounts of attraction versus energy. If the molecules have more energy than the attraction, then they're going to be in the gas state. If the attraction is significantly greater than the kinetic energy, then they're going to be in a solid state. And if they're close to one another, a nice balance, they're going to be in liquid state. So what are intermolecular forces? Well, they are the attraction between molecules. Like interstate is between states. Intercontinental or interoceanic means within, between. There is this very, very, very strong attraction that exists between molecules. Now, this is not the same as the attraction between the atoms in a molecule. That is a bond. That is intramolecular. This is intermolecular, the attraction between the molecules. Now, all molecules have some degree of attraction, and there are four major attractions, but they impact, as it says here at the bottom of the slide, they impact the boiling points, melting points, viscosity, surface tension, and capillary action. We're going to focus in this video, this PowerPoint, we're going to talk a lot about boiling points and melting points, a little bit about viscosity, but I'm also going to throw in a little bit of density there. Later on in the year, we will wrap back around and talk a little bit about surface tension and capillary action, but it's all about this intermolecular forces, how attracted the molecules are to one another. So there are four major types of intermolecular forces. There's London dispersion, there's dipole-dipole, there's hydrogen bonding, which is just it's like essentially a super dipole, and then there's ion-dipole. Now, to make this as generic as possible, there are really three types of substances. There are ones that are charged, those are called ions. There are the ones that are polar, those are ones called dipoles, and then there are ones that are not polar, and that's the ones that are going to show the London dispersion. So if I want to know about the attraction between two substances, say one that is charged, an ion, and one that is polar, that is the dipole, that attraction would be an ion-dipole interaction. If I'm looking at what happens between two different substances, or maybe the same substance in a container that is polar, then those polar molecules are going to be attracted to one another through a dipole-dipole interaction. And hydrogen bonding, again, since it says here, is just a supersized version of the dipole-dipole force. London dispersion is reserved for when there's no polarity, or maybe there is polarity, but there's some other attraction going on. And the concept of London dispersion and dipole-dipole are also referred to as van der Waals forces, where you're talking about what happens when the molecules are attracted to one another in a non-electrostatic way. Okay, so let's talk about each one. Now, I'm going to actually start with the one that is most difficult to wrap your brain around, and that's the London dispersion forces. Okay, so London dispersion forces in the POGL you guys did, they talked a little bit about, this is where they were doing the whole sheep analogy, where the sheep are wandering around the field in a random way, but at one moment in time, some point in time, the sheep may just happen to be on one side of the pasture. So there would be a disproportionate or unequal distribution of the sheep at that point. Well, atoms kind of do the same thing. So if you have atom A, they show things here, atom A and atom B, and the electrons are totally randomly just buzzing around the nucleus, buzz, 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 buzz. But for a short period of time, what happens is atom B, for some reason, just because of total randomness, the two electrons that are in atom B happen to be on the same side of the nucleus. Again, you can understand from a random location, a randomization of locations, that is possible for those electrons to be on that one side. Well, at that one time, what happens is atom A, which happens to be close to atom B, they happen to be in a reasonable vicinity to atom B, will suddenly freak out. The electrons that are in atom A will be repelled by these electrons that are on this side and will push the electrons to the other side. And what happens is atom A and atom B, which inherently, naturally, are not polar, become polar. The atom has a one side that's slightly negative, one side is slightly positive, where the electrons happen to be chilling on one side of the atom, and they tend to make the atoms that are next to them gradually become more polar. That idea of the electron cloud being altered is called polarizability, and atoms or molecules with more electrons are more polarizable. The more electrons, the more that are there, the more polarizable that the electrons, the atoms or molecules are. Now, big picture, all substances have some degree of London dispersion forces as long as they have electrons. So everything but a proton, a lone proton, is polarizable. And the more electrons there are, the more polarizable it is. It's kind of a way to explain why when you have large molecules, like say a I'll use the example, hydrocarbons are definitely absolutely not polar. Hydrocarbons are very, very not polar. Every single one of those central atoms in a hydrocarbon happen to have a distribution of electrons that are very, very even. But as the molecule gets bigger and bigger and bigger and bigger, then the molecule becomes more and more and more polarizable. They show here that some of the things that affect the dispersion forces are how many electrons there are. The more electrons, the more dispersion. The size of the atom. Now, they say size of the atom is kind of a misconception. The atom, as the atom gets larger, there is more there are more electrons, and the more electrons there are, the more polarizable the atom is. There's also talk about the shape. I mean, if the shape is really, really compact, then there's going to be less dispersion forces because you're not going to be able to distribute those electrons very evenly. I mentioned hydrocarbons earlier. Hydrocarbons, like methane gas, is a hydrocarbon. It's a gas at room temperature. Octane is 8 carbons long, and that happens to be a liquid at room temperature. It's what's found in gasoline. One of the compounds that are found in gasoline is liquid at room temperature. And then there's wax. Wax or paraffin is something that's in the order of about 200 carbons long, so much, much larger, much, much more electrons, and it's in a solid form. But all three of them have only London dispersion forces. But as the molecules become larger, the molecules get more electrons, and then the molecules tend to be more polarizable, which means there's more of a London dispersion attraction. A larger attraction means a stronger pull between the molecules, making them overcome that kinetic energy. Polarizability and boiling point they show you here, which is simple, not necessarily molecules, but atoms, neon, argon, krypton, xenon, as they compare to iodine, bromine, chlorine, and fluorine. Now, why did they pick those? Well, those are atoms that have pretty similar molar masses. Well, fluorine, having 2 atoms, is more polarizable. Chlorine, having 2 atoms, is more polarizable. Bromine, having 2 atoms, is more polarizable. So the more polarizable they are, the higher the boiling point. The more attraction there is, the more energy it takes to break them apart. Remember, it says here, remember that the less intermolecular forces, the smaller molecules, the lower molecular weight, and the fewer the electrons. It's all about the electrons. It's more about the electrons than anything else. Okay. Second one, which it actually attaches a little bit to what we've already done, is a dipole-dipole interaction. So whenever you have polar molecules, there's one side that's polar and one side that's not polar. Well, the negative end of one polar molecule is attracted to the positive end of the other polar molecule. So you can see here in the video, in the clip on the right, that the positive ends are attracted to the negative ends, the positive end to the negative end, the positive end to the negative end, and so on and so forth. That attraction is the dipole-dipole interactions. Okay, dipole-dipole interaction. And you'll also notice in this situation, they show some molecules that do repel because they're not aligned very well. On the left-hand side, it's a solid. They're aligned very, very well, so there's very minimal number of repulsions. Liquids, a little bit too much repulsion, so there's not as strong of an attraction. Dipole-dipole interactions, they talk about here how the larger the molecule, molecules of equal masses are more polarizable. They have a higher boiling point. So the more polarizable they are, the more electrons, the more polar it is, the higher the boiling point. And we'll address that closer in a second. Okay, so which have a greater effect, dipole-dipole or London dispersion? Well, absolutely, for the most part, dipole-dipole is going to be stronger because they are going to have that's a stronger attraction, a more of a definite polar nature versus a fuzzy polar nature. It's called an induced dipole. But as the molecule becomes very, very large with a whole lot of electrons, a large number of electrons, what's going to happen is that London dispersion forces is going to outweigh the dipole-dipole interaction. Simply put, big molecules with a lot of electrons are polarizable. They have, as one of the constituents or one of the components that are driving what happens with the substances is the London dispersion. It becomes a bigger and bigger impact the bigger and bigger the molecule is. So now we talked about London dispersion. We talked about London dispersion. We talked about dipole-dipole. Now, I want to address one really weird aspect. Now, let's look at this graph on the right-hand side. You'll notice what they did was they showed you that as a substance, and what they did for each one of these, like for instance, this bottom one is the group 4 combinations with hydrogen. The green one is the group 7 with hydrogen. The blue one is the group 5 with hydrogen, and the red one is the group 6 with hydrogen. So you're noticing from 3 on, boom, 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 group in period 3, as the molecule gets larger and larger, you're going to have an increase in boiling point, which means there's a greater and greater attraction. However, in group 2, okay, group 1 is just hydrogen and helium. In group 2, you got this crazy stuff going on here. You've got the fact that methane is much lower than everything else, and the trend works the same. As you increase the size, it goes up. But for nitrogen, fluorine, and oxygen, those 3 atoms, nitrogen, fluorine, and oxygen, when they're paired up with hydrogen, they have a significantly larger boiling point. And that is because nitrogen, fluorine, and oxygen are very, very, very electronegative. So there is a very strong attraction, but that attraction is significantly greater because that attraction is called a hydrogen bond. Now, in the videos I shared with you, there was a couple times over where it tried to be very, very, very open about the fact that hydrogen bond is not a bond. It is an intermolecular attraction, but it is so strong, it is such a strong attraction, it's referred to as hydrogen bonding. It is not a bond. But what you're looking for is anytime that hydrogen is covalently bonded to either nitrogen, oxygen, or fluorine, that attraction, that difference between the electronegativities is so large that that bond is very, 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 very polar. And since that bond is very, very polar, and better yet, one of the two atoms happens to be hydrogen, which is just a proton as it takes out one electron and it shares it, you've got a very, very, very strong polar attraction. So that attraction between molecules, that intermolecular attraction, is very, very strong. So in a nutshell, anytime you have a molecule that is polar, but one or more of the bonds is between a hydrogen and a nitrogen, a hydrogen and an oxygen, or a hydrogen and a fluorine, that is going to be a special version of dipole that is above and beyond the dipole, which is significantly stronger. And that is, instead of being a dipole-dipole interaction, it's going to be hydrogen bonding. So why hydrogen bonds? Again, because you got nitrogen, oxygen, fluorine have a very, very high electronegativity, and that difference is huge. Here's electronegativity chart. You'll notice, what are the three biggies? Fluorine, oxygen, nitrogen are the big dogs, the ones that have the highest electronegativity. So those are the ones that when they're exposed with that poor little hydrogen, now it has a high electronegativity, but that's because it can act as an anion. But it has just a single electron. So it's good. Those three atoms are going to pull much stronger than anybody else. And then the last type of attraction is ion-dipole, and that is the next level up. Instead of having a dipole, a polar molecule, you have a charged entity. So like I said in the beginning, there's three concepts. There's the charge, there's the polar, and then there's the nonpolar. Charge is like the strongest possible magnet. Dipole is the next possible magnet or electrostatic attraction. And nonpolar are the ones that have to have an induced dipole to have them attracted. This is the biggest force. Of the three major forces, or four major forces, this is the largest one, ion-dipole. And it actually explains why you have some solubility issues. When water, that's what this is showing here, water is very, very attracted to the chlorine ions, chloride ions, and water is very, very attracted to the sodium ions. It will literally rip apart the salt and make it dissolve in water. So this is something that is in one of the books that I found. It kind of is a way to walk through, figure out whether or not what type of forces you have. So you ask yourself first off, are there ions? If they're ions, then yes, you're going to have either ion-dipole or just simple ionic bonding. And then, are you talking about an attraction between an ion and a polar molecule? If you're talking about the attraction between an ion and a polar molecule, that's going to be ion-dipole, ion-polar molecule. If you're just talking about the ions in general, then you actually have the charges being attracted to one another. That's ionic bonding. What if there's no ions present? What if you're just talking about polar or non-polar molecules? Well, the first thing you have to ask yourself is, do I have any polar molecules? If I do have polar molecules, I have to ask myself, wait a second, do I have those special over-the-top types of polar molecules, the ones that have hydrogen bonding, the ones that have hydrogen covalently bonded to a nitrogen, oxygen, and fluorine? If I do, then I have hydrogen bonding. If I don't, it's just normal dipole-dipole interaction. If there are no ions present and there are no polar molecules, the only option I have is London dispersion forces. So what do they have to do with anything? Well, I've addressed a couple times over. They keep talking about in the PowerPoint that I'm using. We talk about the fact that there's this connection between certain physical properties and intermolecular forces. Intermolecular forces is the attraction the molecules have to one another. Well, that will have a direct impact on a couple things, and the ones I want to address here quickly is boiling points and melting points and density. So let's first talk about boiling points and melting points. So in general, and again, this is in general, this is not an absolute, in general, the higher the intermolecular forces, the higher the attraction the molecules have for one another, the more energy that is needed to separate the molecules. So the higher the attraction, the more energy is needed to separate it, which means I have to put more energy into the substance in order to get it to separate, in order to get it to change phases, to go from a solid, which is attracted to one another, to a liquid, or from a liquid to a gas. So in general, again, the higher the intermolecular forces, the higher the melting points and boiling point, because I've had a larger attraction, it takes more energy to separate them out, and the higher the boiling points and melting points. The other thing in general, gross generalization, is that greater the intermolecular forces, the more the molecules are attracted to one another. And the more the molecules are attracted to one another, the smaller the volume they occupy. The closer they are to one another, the smaller the volume they occupy, which means smaller the volume, you're going to have a greater density of the material. So in general, the greater the intermolecular forces, the more dense they're going to be. And then finally, the last thing that is impacted by the intermolecular forces that we want to discuss here in Chem 1 at this point is solubility. Solubility is a matter of how well molecules will be interdispersed with other molecules. And the two molecules that are in place are called the solvent and the solute. Solute is a substance that is going to be dissolved, and a solvent is the thing that's going to do the dissolving. So the example I always give with a solvent-solute situation is, say, Kool-Aid, or anything that contains, say, sugar. Sugar would be the solute. That's the substance that's going to be dissolved. The solvent would be the water. Well, the greater the attraction between the solute, the sugar, and the water, the more likely it's going to dissolve. So sugar dissolves really, really well into water because sugar has hydrogen bonding, and it is attracted to the water, which also has hydrogen bonding. So they're very, very strongly attracted to one another. However, if I take, say, oil, we'll use the example oil and water. I put oil in water. Well, we already know that doesn't mix, but why not? That's because the attraction between the water with its hydrogen bonding and the dipole is very, very limited compared to the attraction between the water and the oil, or the oil molecules, which only have London dispersion. The less attraction, the less soluble. So the more attraction, the more soluble. Okay, so that kind of wraps up. I know this is a very, very long video. It's almost 28 minutes long. So that's a generalization. Again, a lot of this information I know was covered in the previous videos. I just want to put my slant on it as a way to explain with my vocabulary. Hopefully I get this downloaded before our meeting today. Otherwise, I will have one version or another available to you either on OneNote or on my YouTube channel. I look forward to talking to you guys this afternoon. Take care, be healthy, be safe, and see you later. Bye.